Okay, so this is my main topic. This is the one of the major topic which I've been working on for past 2 years, and that is the cooperative path following of robotic vehicles using event-based control and communication. So the outline of my presentation is as follows. So I introduce the problem which I'm trying to solve. There are two components to this problem, one being the path following control design and the other being an event-based cooperative control design. So I also show some of the experiment results which we've achieved in past year. And I end with some open problems and also a video which shows the results which we have. Okay, so when it comes to formation control, I will not really try to motivate why we need a formation control. But something which I will point out to is that most of the literature which we find on formation control assumes that there is always an uninterrupted communication between the robots. There are certain results where this requirement of continuous communication is not necessary, in the sense they analyze what if communication losses happen. And they say, okay, if over a period of time these robots are connected or they are able to communicate, then we can still achieve formation. So what I'm trying to look at is, from the practical viewpoint, trying to communicate all the time, irrespective of whether the communication goes through successfully or not, is not really necessary, because it consumes more power, bandwidth, and this is certainly a problem if you're trying to use a communication medium such as an acoustic communication. So, is it necessary is the question which I try to answer. So one of the most important things is we need methods that reduce the frequency of communication between robots. That is, we want to find methods or use methods where you communicate only when you need, not all the time. So there are results, there is this new method of control called event-triggered or event-based control, which is classified into event-triggered and self-triggered control. And in that, we try to use the event-based consensus algorithms, distributed consensus algorithms, and apply it to the cooperative path following problem, and that's the main core of my research. So the cooperative path following framework is a two-layered framework. One of the layer is the path following controller, which is responsible for motion control of an individual vehicle. So what we have is an AUV or an ASV, an under-actuated vehicle. And we have a desired path, which is parameterized by some parameter gamma. So what this gamma says is it's just a virtual point along the path. Now we specify a certain speed to gamma. So the gamma increments or decreases along this path at a certain speed. So what we want is the vehicle to converge to this virtual point. So when that happens, we have a path following motion control problem. One of the important aspects of path following, which separates it from trajectory tracking, is that what is necessary is just the path that is followed. We do not really care about the time at which it needs to be at a certain point on the path. So how does this convert into a cooperative path following framework? So the same system, we have 3 paths, 3 robots, and 3 virtual points. So in path following, we want the robot to converge to the virtual point. So assuming that the path following is doing its job, what we would want over a period of time is that these virtual points to be aligned. And when that happens, we are able to achieve a formation control. So so the higher layer, which is a cooperative controller, is responsible to ensure that this alignment or the synchronization between the virtual points takes place. And one of the important algorithms which is used here is the first order consensus algorithms. So the main results what we have is a self-triggered approach and event-triggered approach. There are certain issues, so I'll not talk about this in this presentation. What we talk about is much simpler and the most recent result what we have achieved. That is the event-triggered approach to cooperative path following. So I start with the with the path following control design. So here in the presentation, I show the 2D operation, but the extension to 3D is straightforward. It's not anything involved. What we assume is that we provide the linear longitudinal velocity and the angular velocities to the robot as the control input. And there exists some inner loop controller which takes care of this actuation level. So it's able to track the reference commands generated by the path following controller. So the system model what we use is a unicycle model, and we assume there are some kind of disturbances acting on the position of the robot. So Pi is the position of the ith robot. If we consider n robots, then Pi is the position of the ith robot. R represents the rotation matrix, which actually says the heading in two-dimensional case. Vi is the linear velocity, that is the longitudinal and lateral velocity of the robot expressed in the robot frame. And omega is the angular velocity input. So we assume that a reference geometric path PDI is given, parameterized by gamma I, which is a scalar. And we also have a desired speed assignment VD. So we expect in the nominal case that the virtual point progresses along the path at the speed VD. So what is the objective? We want to design the control input UI, which is nothing but the longitudinal velocity and angular velocity of the unicycle robot, or the AUV, such that this path following error, where Pi is the position of the robot with respect to some inertial frame, minus the virtual point. So this error converges to an arbitrarily small neighborhood of the origin. So it just has to converge somewhere closer to that path. Why this arbitrarily small neighborhood will be clear in the next slide. So also what we want to achieve is, in the nominal case, this virtual point proceeds at a speed VD. That's what we want. So what we do is we define an error variable in the body frame of the robot. So it's this error in the inertial frame multiplied by the rotation matrix, the transpose of the rotation matrix, and some constant vector epsilon. So if we take the derivative, we see that the dynamics satisfies this expression, where we have this delta denoted by this matrix. So what we want is this delta to be of full rank. So we want at least the epsilon 1 to be non-zero. If we have this epsilon as 0, then we notice that the angular velocity term doesn't appear in these dynamics. So basically what we are saying is we'll not be able to have a direct control over the attitude or the heading of the robot. And that's the reason we introduced this epsilon. So what we are basically saying is we consider a point which is at some offset from the origin of the body frame. And we are actually trying to control this point and make this point converge to this path. So when this error vector goes to 0, it means the robot itself is converging to an arbitrarily small neighborhood of the path. So what we do is we assign a constant desired speed to the progression of the virtual point. We introduce this V tilde term, which is the term which comes from the cooperative controller. So this adjusts the speed such that the gammas or the virtual points are aligned. And we have introduced an additional term which we call the path following error correction term. So what is the purpose of this? Is that it's important to, it's necessary to achieve faster convergence. So if for some reason, if the robot is lagging behind this virtual point, then this virtual point adjusts itself along the path such that this converges, the error converges to 0 quite fast. And what is important is we assume or we design that this G function is bounded, uniformly bounded. So given the error dynamics, which we've presented in the previous slide, and we say that we do not have the actual error measurement, but only an estimate of this error variable with some estimation error. If we choose the control law as given here, then this solves the path following problem. I'll not go into the proofs, but yeah, in our paper we've, or in also another reference, okay, sorry, I didn't cite the reference here. So it's been shown that this path following controller solves the desired objective. Now we come to the main part, that being the event-based cooperative control. So if we have n robots and its associated paths parameterized by gamma I, and we have the dynamics for this gamma, the virtual points. So what we want is design a decentralized event-triggered control law V tilde such that gamma I minus gamma j, that is the error between the virtual points, goes to 0. It means we need that synchronization. And what is more important is we design some event time instance denoted by tki on agent I, such that each robot communicates and updates its control action only at these instances. So what we are trying to do here is eliminate the need to communicate all the time. We somehow design these event times when the robot communicates. So first order consensus, this is standard first order distributed first order consensus algorithm, which is used in many places. So if we have a single integrator agent using this control law, where gamma j is the value of the neighbor of agent I, which can be collectively written as minus L times gamma, where L is the Laplacian of the graph. So using this control law, we can always guarantee that asymptotically the values of the agents converge to an average value. So a consensus is achieved. So all the agents agree to a certain value. What is the assumption here is that you have continuous availability of the neighbor states, which means you are measuring or you're communicating with your neighbors continuously, and you have its value at all time so that you can compute this control input on every agent. Now that is exactly what we want to eliminate. So we refer to the event-triggered consensus literature, where they modify the control input in such a way that is the same control action, but instead they use the values of neighbor at only the event time on agent I. So let's look at this from a perspective of agent I. So what it does is somehow it has generated an event time tk, and it records what its value is at that event time. And it also somehow has its neighbor's values at its own event time. And so it implements this control input, and it holds it constant until the next event time. So how do we exactly generate the next event time tki? So we define an error variable, which is nothing but this term minus the continuous value of the same term. So this is a constant until in between these event times. This is constant. This doesn't change. But in practice, in reality, the continuous evolution of states does happen. So we compute this error value, and whenever the error value becomes larger than this term, we trigger an event. So you trigger an event, you measure the states of your own, or you measure your own states and also the states of the neighbor. You update the control input and continuously monitor this condition. When this violates, you trigger another event, update the control input, and the cycle repeats. So what we do in the event-based cooperative control is use the same event-triggered consensus law and use that as this cooperative control input. Of course, we have these two terms, but we use the cooperative control law for the V tilde term. And we use the very same error variable or the event trigger condition to generate events. So what we are able to show that the results of event triggered consensus also holds in case of an event-based cooperative controller. And eventually it achieves synchronization of these variables gamma I. But the problem here is to compute this error condition, we still need the value of the neighbor. And that still means that we have a continuous communication. So what we have achieved until now is an event-based control. We still assume that we are able to measure continuously, but we just update the control values at specific event times. Now, how do we transform this from event-based control to event-based communication? So for any agent I, what we say is when an event is generated, it transforms it broadcasts its own event time, its state value at the event time, the cooperative control input which it generated at its own event time, and also this path following error correction term value. So it just broadcasts and assumes that its neighbors are able to receive these values. So consequently, what happens is agent I also receives the similar values from its neighbors. Now we know that the cooperative controller input is held constant between the event times. That doesn't change. So what agent I does is, over this time interval, it estimates the neighbor's value. So the neighbor has transmitted its state and its control input. So basically what agent I does is, it uses the same values, and since this value is constant, the integration is kind of straightforward. It simplifies. So it is able to estimate the values of its neighbors. So using this estimates in the event triggering condition eliminates the need to communicate continuously. Now we have an event that is generated. Once the event is generated, the agent computes its own control law, holds it constant until the next event time, broadcasts this entire packet to its neighbor so that its neighbor can estimate its own state. So what it does at every sampling time is estimate its neighbor's state as well and uses this condition to generate an event. So now we have an event-based control and event-based communication both together. So this is the entire schematic of our system. So as I said, there is a path following controller and there is a robotic vehicle. So this is doing its job. From the network, it receives a packet from the neighbors. It also transmits its own data to the neighbors at its event time. So there is this triggering condition which I showed in the previous slide, which is continuously monitored, and it decides when to generate an event. Once the event is generated, the event-based consensus control law is executed. The correction input goes to the path following controller, and then we have this collectively we have this cooperative path following, an event-based cooperative path following. So the experimental results, we validated the approach using 3 AUVs from LSTS lab. And we gave a circular path to each of the AUVs. So here you can see the path following error, longitudinal and lateral. So it converges not to 0, but because of the noise around the neighborhood of 0. In lateral, you can see some oscillations that was mainly due to the currents and the cross-track error which we had. So here you can see the virtual points, that is the gamma of all the 3 robots. So initially, they started different initial conditions here, and they eventually achieve consensus and they grow. What we did in between is we modified the speed of one of the AUVs. We just slowed it down so that we show that there is a reactive action on all the other vehicles. So you can see that the other vehicles too are adjusting their speed according to the emulated or failures on one of the robots. So AUV1 changes its speed. So as a result, because of the consensus law, you can see that the other agents also, other robots also change its speed accordingly. And our main result is shown here. So this is the plot of time and the event time here. So you can see the simulation, the experiments were conducted for 617, 643, and 648 seconds respectively for 3 AUVs. And the maximum inter-event time was 160 seconds, 32 seconds, 32 because here you can see that no other event occurred. So it's much more than 32. And 78 seconds. So this means that we didn't have to communicate for example, AUV1, it didn't have to communicate for somewhere in between for 160 seconds and still achieve the formation. So the number of events generated on every vehicle, you can see here 31, 36, and 51 events. That means so many number of communications. So if we had to communicate in a periodic fashion at a sampling frequency of, say, 0.01 seconds, so for 617 seconds of experiment, we would have to communicate 61,796 times if we were doing a continuous or a periodic communication. But with event-based, we've reduced it to just 31 events in this case in the experiment results. So that's like just 0.05% of the communication. So that we think is a significant reduction in the amount of communication required while still achieving the formation. Now I would like to show the video. So here, all the 3 AVs are following a straight line. So they enter into the path following mode at different times. And then when one is ahead, it slows down, and all of them achieve a formation and they proceed. Similarly, for a circular formation. So the same circular formation now, actually, the experiments. So that was the recording of the Neptus console. And here, maybe it's not clear. So one AUV is there, the other one is here, the other one will appear somewhere here now. Yeah, here. So as they pass, you can see they are in a radial alignment as they move around the circle. So again, it's the same recording of the console, and you have the vehicles here. So in continuation with this, what we are also trying to work on now, and we have some simulation results, is the event-based coordinated moving path following, where the path is not stationary anymore and it moves along with the target. So the path is expressed with respect to the target. And this is just the simulations where, again, we are using event-based communication, where the 3 robots need to circle a target as the target moves. So yeah, this is a simulation. Of course, the robots are quite fast. May not be possible in reality, but So one of the main problem with this event-based communication is we are trying to communicate only when we need to. So what if we are not able to communicate we want to? So there is an event generated and there is a broadcast that happens, but the other agent doesn't receive it. So what happens then? So we did some experiments where we simulated or we introduced communication losses. It seemed to work, but we still didn't do elaborate experiments. So we also need to do a formal investigation as to what happens if there are packet losses or communication losses and delays, and arrive at some proofs that it still works. And delays can play a very important role when it comes to the underwater acoustic communications. So another interesting was now we are having some kind of a static formation. What if the formations can change dynamically? That would have implications in the sense that the communication graph is also dynamically changing now. And in such cases, the event-based control and communication approach that we presented cannot be applied directly. So that is one of the interesting direction which we can. Questions? Thank you.
So I was wondering, at the beginning you assumed it's full action in terms of angular velocity and linear velocity. But your vehicles are not fully actuated.
No, it is not fully actuated in the beginning.
So your U, what is in U, the linear velocity and angular velocity?
Here? So you can see that there's the lateral velocity is 0. Vi is the linear velocity where you can only actuate the longitudinal. Yeah. Yeah.
Okay, so I guess the second question I have is like when you're doing like your path following in a circle, what if your desired velocity around the circle is larger than, for example, the outgoing circle?
I'm sorry, I couldn't get.
So if your desired velocity is too high, so the outer vehicle can't follow that, does the event, does the consensus algorithm basically slow down everything to satisfy the constraint?
Not really sure how that works because the desired velocity, what we specified, is something that is feasible for the robots to follow. So in case if the outermost robot is not able to achieve, we didn't verify this in experiments, but if the outermost robot is not able to achieve its desired velocity, then this term kind of kicks in and it slows down the velocity of the gamma. So eventually what we have is the path following works the way it is supposed to. So we have this some desired velocity and this gives the correction term such that the virtual point itself slows down according to the robot. Now, when we have a constant communication without the event-based part, then the consensus algorithms do take that into account and they kind of adjust all the other vehicle speed. But with event-based, that's one thing what we show here is that one of the AVs changed its speed. The others do not know that AV has changed its speed. But with event-based, it is still able to adjust its velocity. Now, what is the amount of changes that can be tolerated? It's kind of a competing objective between the G term in the velocity and also the cooperative control. So there, when we try to do a more radical change where AUV1 stops completely, the other guys do slow down, but then there is some misalignment between the robots. So the others just do not go ahead, but they're not in the formation either. They don't completely come to a standstill. So, yeah. So there is some amount of adjustment for the speed. No, it's Wi-Fi. Here, we perform the experiments on the surface where Wi-Fi was used. If we want to go to the acoustic, then yes, there we need to consider delays and possibilities of no two-way communications, or they should not communicate at the same time. I'm not really sure, but we need to look into the communication medium and the hardware what you use, how its limitations are, etc.
So here, I see tau k. Tau k here is the duration between two consecutive communication.
Yes, two consecutive events, which also means that the communication time.
So here, you mentioned tau k here for the case of AUV2, 0.03 second, right?
That's the minimum inter-event time. And our sampling time was 0.01 seconds. So the minimum inter-event time is less. So obviously when we are in the transients, we need to communicate more to achieve formation. Once we have achieved formation, then we do not need to communicate as much as in transients. So here you can see when we introduce this this error in AUV1, you can see there are more events at that point, so that the other AUVs react to it.
Since I don't fully understand some of this, I just know that this is just coming from a networking background. Have a look at the Draco algorithm and the consensus protocol,
Mm-hmm.
because that's more or less what you want to do generically. It's standardized, used and tested. Even in the situation with link losses and delays, they find an agreement between those. And they also freeze or use the normal communication based on changes.
Okay.
So that might be interesting.
Yeah, maybe I'll talk to you after this presentation, and then I think we can look into what that is. Yeah. Thank you. Thanks for the suggestion.
So another question, what do you mean duration in that?
That's the total experiment time. So from the start of the path following to how long the experiment were conducted. So the AUVs were circulating for 17 seconds.
So this should be the same for all vehicles.
No, because the path following for all vehicles, they do not enter simultaneously into the path following routine. You launch AUV1, it enters into path following, then AUV2, AUV3. So these do not enter their respective circles at the same time. In simulations, yes, but in practice, no. So they have different. So the thing what we are trying to specify here is, you can see that these AUVs start communicating with each other and enter into this cooperative path following mode at different instances of time. They do not start simultaneously.
So what about the environmental disturbance when you incorporate it into your control approach?
Uh,
You
it-
have to look into that.
environmental in the sense the
The currents or
currents. Yeah, that's one thing which we prove in the path following controller. Sorry. Okay, so yeah. We consider there is some kind of disturbance acting, and we prove input to state stability, to be precise. That, okay, we do not converge, the path following errors do not go to 0, but some bounded region around 0. That's what we prove. Are we estimating some kind of disturbances acting on the robot and then acting on it? No, we are not doing that. And that's the reason you could also see the lateral errors, which are not 0.